Then henceforth we have to discuss the design of a socket, right? Now what are the stresses acting on the socket? Now again we have to remember that we are designing this Cotter joint by assuming that complete assembly is subjected to tensile load. Complete assembly is subjected to tensile load, and due to that tensile load, what are the chances of failure? Now if this complete assembly is subjected to tensile load, what are the modes of failure of this component socket? So that we have to find out this diameter we have found out by considering tensile load. Now we have to find out this diameter and this diameter, right? So what are the chances of failure at this portion? This portion will try to be filled by, this portion will try to be filled by tensile failure. So that tensile failure of socket is equal to applied force divided by cross-sectional area. Now what is the cross-section at this point? So let's assume this socket have some hollow portion to insert the rod, right? Remember that while drawing the cross section. So this is the hollow portion which is available beyond the slot made for the inserting the cutter. So right, this is the hollow portion. So if we cut this portion at the slot to tensile failure, so if at this cross section, what will be the area of the area under the tensile failure? So this is the outer circle. For example, this is the outer circle having this dimension. So what is this dimension? This dimension will be available from the assembly drawing. So what is this dimension? Diameter D1, right? This slot is having diameter D2, right? And it is inserted, the cotter is inserted into the slot. So from this diagram, if we get in outer diameter is diameter D4 and the inner diameter is diameter D2. Now if this is internal diameter D2, right? This is internal diameter D2. Now what is the external diameter? Again I'll repeat, this is diameter D1, right? So capital D1 is small d1 is the diameter of that rod. So this is capital D1, and how much is the area subjected to the tensile failure? So this area. But again remember, in this area there is a slot. So if we cut this material and see from this side, this is the cross section which will looks like. So at the slot there is no removal of the material, so the cross section will be like this. Understand? So what is the area of this cross section? So area of this cross section will be equal to pi by 4 into d1 square minus d2 square. So how much is this area? Now from pi by 4 d1 square minus d2 square, so we have with us this much of area. Out of that area we have to remove the area of this slot. So how much is the area of slot that we have to remove? This is having thickness t, right? So how much area we have to remove from that is minus, if I minus this d1 minus d2, d1 minus d2 multiply by thickness t. So this is the area we have to subtract from the cross section area of the circle. So from this equation, diameter d2 is known, thickness t is known, d2 is known, only unavailable is diameter d1. So from this equation we will get diameter d1, that is diameter d1 of the socket. So second highest diameter of the socket, sigma t. Again sigma t is equal to syt upon factor of safety, right? This syt, now mark my words, this syt is for the material for the socket. So in some cases some designer selects material for whole Cotter joint as plain carbon steel, and in plain carbon steel also some designers select different material for SPIGOT, some designers select another different material for the socket, and the material for the cotter is another third different type of material. So majorly most of the designers select plain carbon steel only, but having different specification for spigot, socket and cotter, right? But and according to that selected material we have to find we have to replace SYT from the design data book, right? And generally in case of university examination, SYT is given in the problem itself. Factor of safety is, again we have discussed, it is 4, in between 4 to 6. So if applied force is known, sigma t is known, from the given cross-sectional area, only unknown parameter was diameter d1. So from this equation we will get diameter d1 for socket. So remember we are designing a socket. Then crushing failure of the socket. Now crushing. What is mean by crushing? Now again, the failure of socket and spigot is near about same. Now this cotter when is subjected to tensile load complete assembly, this cotter will try to crush the slot, or slot will try to crush the cotter. It is vice versa. So crushing takes place here at this slot, right? So what is that slot? So if you see, there is a whole slot of up to diameter d4, right? But as there is a hole of diameter d2 in between that, so how much is the portion which is subjected to a crushing? Only this much portion that is subjected to crushing failure of the component. So how much is the area subjected to crushing? So crushing failure, so we have to project that area, that is applied force, then d4 minus d2 into thickness t. What is that area? Area d4 minus d2 into thickness t. So this much is d4 and we have to subtract this area d2 and multiply by t. So this area shown by hatching line will be subjected to crushing only due to cotter and compressive load acting on this component. So from this equation, diameter d2 was known, diameter d4 was known, and diameter d2 was known. Sorry, for d2 is known, dt is known, and d4 was unknown. So from this equation we will get diameter d4 which was unknown if force P is known and sigma CR is known. Again, sigma CR is equal to SYC divided by factor of safety, where SYC is the material for socket, right? Now next type of failure is shear failure of the socket. Now if you see in this diagram, due to extreme crushing, this portion of the collar will get sheared off when compressive stress is increased on the collar, right? So this, when this crushing is increased, this cotter will try to come out of the collar of the socket. So if you imagine this socket collar will get sheared off. So what is that shear failure? So if we draw a portion of socket collar like this, what is the diameter of the collar? Now diameter of the collar is, we have considered this is equal to diameter d4. Now the central diameter, and there is a central hole or central slot having diameter d1. So this much portion will trying to get shear off. This, what is the dimension of this? This dimension is equal to C. So from where it is got, if you remember the assembly diagram, this is equal to C, right? This dimension is equal to C. This cotter will try to shear off this much portion, this much and this much. So how much is that? External diameter is d4, internal diameter is d2. So this portion at this place and this place will get sheared off. So how much is that portion? That we have to discuss. So what is the shear failure? Shear failure is equal to direct shear. This is which kind of shear? Direct shear. So applied force divided by shear area. So what is shear area? It's a rectangle here. So it is equal to d4 minus d1, right? So how much? d4 minus d1 into how much? Into C. So in this d4 is known, d1 is known, only unknown is diameter, dimension C, that is the distance from the slot distance from the slot to the end of the collar, this distance is equal to C. So this much is the shear failure of the socket. Again, applied force will be known. Direct shear is equal to SSY upon factor of safety for socket material. SSY and factor of safety we will select for the basis of material and application, and from this equation we will get dimension C. Next one is the double shear of Cotter. Now we have considered up till now 10 failure, out of which 6 failures were for SPIGOT, 4 failures were for socket, and now we are going to consider the failures for Cotter. Now by which mode this Cotter will be trying to get failed. Now to understand that, if you consider the assembly diagram for the for the Cotter joint, now this SPIGOT gets inserted into the socket, then we insert a Cotter into that particular socket joint, right? So I have to adjust the slot, and when this Cotter gets inserted, it will be pulled by these two rods, or it is subjected to tensile load. So when it is subjected to tensile load, it will during the assembly it will be sheared off from the point of connection. So what is that point of connection? If you see the assembly diagram, so I will clear off this. So if you see assembly diagram, from this point, at the point of connection of the Cotter with the SPIGOT and socket, this portion will shear off. So shear off means it's get sheared off, and it is divided into two portions, so that is called as double shear failure. So what is that double shear? So that double shear is if we draw the diagram of that complete Cotter will be like this, right? This is a center line. If I draw a center line, and this much is the diameter D, that is this diameter D, sorry, diameter D2, right? Now it is getting sheared off from here and here. So if it is having thickness T, so from here it is getting sheared off, and from here it is getting sheared off. It is called as a double shear. So this is equal to B and this is equal to T. So what is the equation of the shear? Tau is equal to, again this is called as double shear. It happens because of applied force, and hence B into T, this is one shear, and again B into T, this is second shear. And this is the example of double shear. So from this equation, T was known to us, only unknown parameter was width of the Cotter. So from this equation we will get width of the Cotter, right? So for that width of the Cotter, applied force was known. Direct shear is again SSY upon factor of safety, and SSY upon factor of safety, this is now for which material? Material of the Cotter. If it is a different material, we have to put yield strength in shear for the Cotter, right? This is called as double shear failure. From this equation we will get width B.